Our story begins about 4.6 billion years ago. Imagine a vast, swirling cloud of gas and dust called a nebula. This wasn't just any nebula, this was the solar nebula, the birthplace of our sun and all the planets that orbit it. Gravity, the master sculptor of the cosmos, began to pull everything in the nebula toward the center. As the cloud contracted, it spun faster and faster, like a figure skater pulling their arms in during a spin. At the heart of this cosmic whirlwind, the pressure and temperature skyrocketed. Atoms of hydrogen, the simplest and most abundant element in the universe, were forced to fuse together, releasing unimaginable amounts of energy. And just like that, a star was born, our sun. The sun's birth wasn't a solo act. The remaining gas and dust continued to swirl around the newborn star, forming a disk. This disk, called a protoplanetary disk, would become the stage for the formation of the planets, including our own Earth. In the protoplanetary disk, tiny dust grains, remnants of the original nebula, were constantly colliding and sticking together. This process, called accretion, is like building a sandcastle one grain at a time. As these clumps of dust grew larger, their gravity increased, pulling in even more material. Over millions of years they grew from dust grains to pebbles to boulders, and eventually to objects the size of mountains. These planetary building blocks are called planetesimals. The inner solar system, closer to the sun, was a hot and volatile place. Lighter elements like hydrogen and helium were blown away by the solar wind, leaving behind rocky materials like iron and silicate. This is why the inner planets, including Earth, are rocky planets. Further out, beyond the frost line, temperatures were cold enough for ices like water ice and methane ice to exist. These ices became incorporated into the growing planetesimals, allowing the outer planets to grow much larger and become the gas giants we know today: Jupiter, Saturn, Uranus, and Neptune. Back in the inner solar system, the young Earth was far from a peaceful paradise. It was a hot, molten world, constantly bombarded by asteroids and planetesimals. One of these collisions, however, would have a profound and lasting impact on our planet. A Mars-sized object, which scientists have named Theia, slammed into the young Earth with incredible force. The energy released in this collision was unimaginable, enough to vaporize rock and melt a significant portion of both objects. Debris from this cataclysmic event was ejected into space, forming a ring of molten rock and dust around the Earth. Over time, this debris coalesced under its own gravity, eventually forming our moon. The moon's formation had a stabilizing effect on Earth's rotation. Without the moon's gravitational influence, our planet's tilt would be much more chaotic, resulting in extreme and unpredictable seasons. Section 4. Earth's Inner Fire, From Molten Mass to Layered Planet. The giant impact that created the moon also had a profound effect on Earth's internal structure. The energy released during the collision melted a significant portion of the planet, turning it into a swirling ocean of molten rock and metal. As Earth began to cool, heavier elements like iron and nickel sank towards the center, while lighter elements like silicon and oxygen rose to the surface. This process, called differentiation, led to the formation of Earth's layered structure. At the heart of our planet lies the inner core, a solid sphere of iron and nickel under immense pressure and heat. Surrounding the inner core is the outer core, a layer of liquid iron and nickel. The movement of this liquid metal generates Earth's magnetic field, a protective shield that deflects harmful solar radiation. Above the core lies the mantle, a thick layer of hot, solid rock, but one that can flow very slowly over geological time. The outermost layer is the crust, the solid, rocky surface upon which we live. Section 5. Air, Water, and the Shaping of a World. As Earth continued to cool, gases trapped within the planet's interior were released through volcanic eruptions, forming the early atmosphere. This early atmosphere was very different from the one we breathe today. It was mostly composed of carbon dioxide, nitrogen, water vapor, and other gases. Water vapor in the atmosphere condensed and fell as rain, filling the low-lying areas on Earth's surface and forming the first oceans. These early oceans were acidic and hot, but they provided the cradle for life to emerge. The early Earth was bombarded by asteroids and comets, some of which carried water ice. This bombardment, along with volcanic outgassing, contributed to the growing oceans. Section 6. A Planet Finds Its Balance, the Dance of Continents and Oceans. While the surface cooled and solidified, the intense heat within Earth continued to drive geological processes. The Earth's crust is broken into large pieces called tectonic plates, which float on the semi-molten mantle below. These plates are in constant motion, driven by convection currents within the mantle. They collide, pull apart, and grind past each other, giving rise to mountains, volcanoes, earthquakes, and the very shape of our continents. Over billions of years, the continents have drifted across the globe, breaking apart and colliding to form supercontinents, only to break apart again. This continuous dance of the continents, known as plate tectonics, has shaped Earth's surface and influenced the evolution of life.